All right, so today we're going to talk about the array representation of binary trees. And the really important thing to understand here is that the array representation of binary trees is better, like basically across the board, but it's really, really bad if you have an unbalanced tree. So that's, if you're going to remember anything from today, remember that. You can do a binary tree without any pointers at all. But you got to make sure it's balanced. If you don't have a balanced tree, you're going to get into trouble. So let's begin. And you might think it's like impossible, like the array BST. You might think it's like, how on earth could you do this without news and pointers and stuff like that? But I'm telling you, like you can do all of this stuff just in a vector. Yep. And let's put some numbers in here. 40, 20, 10, 30, 60, 50, and 70. Okay, so we've talked before about a DFS a little bit. DFS is that print function. When we recursively print, we go down to the left as far as we can, and then we kind of do this pattern here. That's a DFS traversal. Okay. Depth first search. What we're going to be talking about today is something called BFS, which stands for breadth first search. And that basically is kind of like as you're reading a textbook. Okay, so we're going to call this person 0, 1, 2, 3, 4, 5, 6. So we're just basically just reading the tree from left to right. And then this guy's kid here, which would be, I don't know, 0 or something, would be 7. His kid would be 8, 15, 25 would be 9, 35 would be index 10, 45 would be 11, kind of running out of room here, 55 would be 12, 65 would be 13, 80 would be 14. Okay. So these numbers here are the indices in the array, because we are going to convert this bad boy over here into an array that means the exact same thing. So if you're ready for this, this is how we convert a binary tree with all these pointers and null pointers, and there's a root pointer and all this stuff. We're gonna just put it into basically just a vector. Okay, so 40, 20, 60, 10, 30, 50, 70. Uh, 0, I guess. I don't know. 0, 15, and then dot, dot, dot. I'm not going to do the rest. Index 0, 1, 2, 3, 4, 5, 6, 7, 8. Now, there is an algebraic relation. You might be wondering, like, what? So what we did here, this is called a BFS. So BFS goes like this. So you're like reading across the tree left to right and top to bottom. So when you finish one row, one level in the tree, you go down to the next one. And what we've done here is actually just put the root into index 0. We put the left child of root into index 1 in the vector, the right child into index 2 in the vector, and so on and so forth. And there's an algebraic relationship between every node and its kids. So for example, 4 here, his left child is 9, and his right child is 10. For 5, his left child is 11, and his right child is 12. And so if the parent is 5, and the left child is 11, and the right child is 12, can anyone figure out the pattern here? So if the parent is 2, the left child is 5, the right child is 6. Can anyone see the algebraic relationship between the index of a parent in the array and the index of the children? Good. Good. So the index of the parent, let's say 5 is the parent here. The left child is 2 times the parent plus 1 is the left child, and 2 times the parent plus 2 is the right child. So from the root, 2 times 0 is 0, plus 1 is the left child is 1, plus 2 is the right child is 2. If we're here, 2 times 4 is 8, plus 1 is 9, 2 times 4 is 8, plus 2 is 10. And so you can get the index of your kid. You don't need a pointer. If I am here, if I am at index 2, I know that my first kid is going to be at index 5 and my second kid's at index 6. So if you see here 60, his left kid is 50, his right kid is 70. No pointers necessary. You don't need any pointers at all. You just have a vector of integers. And if you want to get your parent, that's also really cool, because with a binary tree, you would have to have a pointer back to your parent, maybe. And so that pointer is also going to take up RAM, but we don't need that. Like if we want to know what the index of our parent is, we can do that by doing the algebraic equation the other way. So if we solve for p, we say p is equal to L minus 1 divided by 2, or p is equal to R minus 2 divided by 2. And if you are clever about it, you actually don't need to know if you're the left or the right child, because you can do a floor operation. So if you just use this one, take your index minus 1 and divide by 2, because this is integer division, that's the floor operator there. Then sorry, the floor would cover the whole thing. But we're doing integer math, so we don't need it. So basically, if your index is, let's say, 12, 12 minus 1 is 11, 11 divided by 2 is 5. If we're here at index 9, 9 minus 1 is 8, 8 divided by 2 is 4. And so you can find out the index of your parent via algebra. So if you're here, you can find out who your parent is, you can find out who your kids are. It's really cool. Like if you've ever been curious who your parents are. Quotes taken out of context in computer science. Okay, so so if you yeah, that's really nice. And what's really, really nice about this is actually, well, there's two things that are actually really, really nice about this. The first thing, this is contiguous in memory. Okay, so this is a contiguous block of memory. These pointers could be anywhere in RAM, right? Like this guy could be over here, and then his kid could be like over here, and this guy could be like way over here, and this guy could be like way over here. When you load from RAM, it tends to load about 8. It loads what's called an entire cache line at once. It loads like maybe 8, maybe 16 integers all at once. And so if you've got all of your array laid out like this, when you do one load, it's going to give you all that in one load, right? And so with this, you have to load one number, and then you load from another chunk of RAM, you get another number, and you load from this guy, and you get another number. And a load can take a long time. A load can take like 100 cycles. In other words, you could do like 100 adds or 100 subtracts in the amount of time it takes you to do one load. A multiply, by contrast, is usually about 4 cycles. It could be more, it could be less, but that's just a good benchmark for us. And an addition is 1 cycle. So traversing a binary tree like this, if you're getting if your binary tree is not contiguous in memory, then what happens is that you're going to spend the amount of time equal to like 100 adds in the amount of time it takes you to get to the next node. And then it takes 100 more cycles to get to the next node, and 100 more to get to that one. Whereas here, you got to do a add and a multiply. And since it's a multiply by 2, you actually can get away with it with 0 cost, actually. So it's about 1 cycle to do this. So traversing a tree when it's in array form is going to be a lot faster, like probably an order of magnitude faster. Now, you know, this thing here, like your system will try to put it contiguous in memory, but if you're deleting things and moving things around, then it won't be. So this performance probably isn't as bad as you think it would be, but there's no guarantee it's contiguous. But when you got contiguous memory like this, and you don't have to do these pointer dereferences every time, yeah, in practice, this will be much, much faster, even though the big O is the same, right? The big O is the same. Like if you want to find 80 here, you go to the right, go to the right, go to the right, and you're here. and you go to the right, and you go to the right, and you go to the right. It's still for operations, but those operations in practice are actually going to be much faster. Okay, this is kind of more of a CSI 45 talk because we're actually talking about real world performance and things like that rather than big O. But that is actually a big reason to use the array representation of a binary search tree. There's also another good reason, and the other big reason is less RAM. Okay, there are 4 bytes and an int. How many people are still alive on chat right now? They're 8.8. Okay, we're on a 64-bit system, so a pointer is 8 bytes. Okay. All right. So Tipton, if we have a node, like let's say we're in a binary tree and we got a left kid, we got a right kid, and we got a parent pointer, and we've got an integer in here called data, which I can't fit within that box, but let's pretend you could read that. How many bytes is this one node going to cost? We're just looking at a single node in the binary search tree. We got 3 pointers and we got a data payload that is 4 bytes big. How much RAM does one node in the classic pointer-based binary tree take up? 28 bytes. That is correct. So it'll cost 28 bytes. So Messick, what is going on here is we are going to hold this whole binary tree in an array with no pointers at all. No pointers at all. We're just going to use a vector. But it's going to be a binary tree, but it's a vector. So there's no pointers. Okay? So Messick, how much RAM, if we got a vector and we got this guy, and he's just the number 8 or something like that, how many bytes does that one element of the vector take up? We're just holding a single integer with the array representation of a binary tree. How many bytes to hold one integer? How many bytes to hold one integer, Messick? One integer. How many bytes is it to hold a single integer? 4. Very good. Okay. So in the standard pointer-based system, the pointer BST, the pointer sisters, it takes 28 bytes to hold one integer. Because you got the integer, which is 4, and you got 3 pointers for the left kid, the right kid, and the parent. If you're fairly profligate, you can actually cut that down. You obviously don't need the pointer node, but let's just say you need 28 bytes to hold one number. Whereas under the array representation, an array-based BST, you need 4 bytes. Which is cool. That's way smaller. That's like, that's 7 times smaller. Like, that's pretty good. That's pretty good. You're 7 times more compact in memory. Okay. So less RAM. It's faster because it's contiguous. It's faster. It's contiguous. Okay. So what is the downside to it? Well, the downside is that your tree had better be balanced. Because if it's not, watch what happens. Okay. So if we had an unbalanced tree like this. All right. And we wanted to put it into an array. Got 10, 20, 30, 40. Hockman, what index does the root go into? We got our standard pointer-based BST up here. We're going to put it into the array representation over here. What index does 10 go into? 0. Very good. All right. And then what index is its right kid? Remember the equation. Left is equal to 2 times the parent plus 1. And the right child is at the index of 2 times parent plus 2. So what slot does 20 go into in the array? And you got to mark, because there's no left kid, right? You got to mark that as being like not used. Yeah, so 20 is going to go into index 2. Yep. Now his left kid is marked off, but also both of the kids of whatever the left child here are also marked off. So there's actually 3 blanks And then this one is going to be an index 2 times 2 plus 2 is 6. 2, 3, 4, 5, 6. Good, I did the math right. And that is 30. And then the kid of 30 is going to be 2 times 6 is 12, plus 2 is 14, 7, 8, 9, 10, 11. 8, 9, 10, 11. Whatever. 14. So 40 is over here. You guys see how much wasted space there is now? So to hold just this binary tree with 4 people in it, we get exponential growth in the size requirement. So if you have an unbalanced, you get boo performance, right? You get order 2 to the n space requirement. And I don't think we've talked about space requirements before in this class, just because it's usually order n, right? If you need to hold n people in a linked list, you use n memory. If you need to hold n elements in a binary search tree, you use n memory. Like as the number of elements you store goes up, the amount of memory you use goes up with it, linearly, proportionally, right? This is an order exponential memory usage. And so, yeah, so there is big O for space as well. And so unbalanced trees would be really, really bad for this, because each time you go down, the index doubles. So you got to make sure that your tree is full and completed and as balanced as possible, as humanly possible. If you use a vector of ints, what do you use for null nodes? I would probably either make a class out of it. So you're storing like a struct that has like an int data and like a bool, is valid or something. You do that. It's wasteful. It's quite wasteful. It'll actually double your RAM requirement if you do that. A better way of doing it is to use a bit vector. And so, in addition to the vector of integers, you'd have something called a bit set. And then the bit set would track basically what you have here, down here below it. You can think of it metaphorically below it. It's not literally below it. Like, you can think of it that way. Is true, false, true, false, 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 true, false, 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 true, false, false. You understand? The bit set uses 1 integer for every 32 integers you have, so it's not bad. It's going to add one. It's going to increase your memory requirements by 1 32nd, whatever. It's going to be way, way more efficient than a pointer-based system. You just basically have true or false, or you can use a magic number. Like if you're really feeling like, saucy, you could just have a magic number. Like, okay, we can't store -800 in this binary tree. It's just not allowed. and then you indicate that something's not used by writing -800 into it, and that means there's no data here. If you're really feeling like gutsy, like, you can do that and cut down your memory requirement a little bit. I don't recommend it. Because at some point, somebody's going to be like, I'm going to store -800, and it just doesn't work. And they're like, what? Why can I not put -800 into this? Of all the numbers, -800 doesn't work. You're just like, oh, I needed some number to indicate an empty spot. So doing a bit set is the you just got to pick some. Like if you're doing the magic number route, like you got to just pick some number, and that means there's nothing here, and you've got to give up one of them. And at some point, somebody's going to try to store it, and then they're going to get mad at you. So the bit set is probably the correct way to do it. And you can look that up on CPP reference. It's literally called bit set. Okay, so yeah, the space requirement is bad. If it's unbalanced, the running time is crap. It's going to be order n for insert, search, and delete. Again, this is for an unbalanced BST, right? This is for an unbalanced An unbalanced BST has horrible running time, right? Because it's a linked list but worse, right? So if you want to add something, you go to the right, go to the right, go to the right, go to the right. So if you have 1 million people in your binary search tree, you go to the right 1 million times to insert at the bottom. It's not good. It's really not good. So, and the space requirement, if you're doing the array representation, is 2 to the n. So, you're holding, 500 integers, and you used 4 gigs of RAM to hold 500 integers. So instead of 2K. So it's really bad if it's unbalanced. Okay. And so what we're going to learn on Wednesday is how to make something. We're not going to learn a balanced BST. Actually, that's a junior level topic. I will toss that ball to the Seaside 115 people at Fresno State or wherever it is you guys end up going. But I will be showing you a data structure on Wednesday that is a binary tree. It's not a binary search tree. It's a binary tree, though, that is always full, complete, and balanced as possible. Okay. You forgot that magic numbers had a name. Yeah, it's a very common hack in computer science because we don't want to make a second data structure. It's annoying to keep everything synchronized with each other, and so if you look at some of my code for a threading library I created, if the thread died or something, it returned negative 700 or just some number that just because normally you can return a value from a thread, and I just would return some magic number, and the random testing they did crashed. They randomly guessed the random number that I'd picked for the error code. So true story. C'est la vie. And if you think that's just me, that's literally how Unix and Windows do things as well. They have, if you look at the return code from a thread or something like that, Unix only allows int main, right? You know how we have int main, right? Your int main hello world, your first line of your program, int main, right? The int is not actually an int. It's not an int. It's only a char technically under the POSIX standard. Only the last 8 bits are used because the upper bits I think are used for magic number kinds of nonsense like threads dying and stuff like that. Yeah, Windows I think has different magic numbers for different things, and it's not just me. It's not just me. It's not just bad programmers. Microsoft does it too. Although maybe I'm repeating myself. I don't know. Okay. So that is the array representation of a binary tree. Let's maybe do a little more practice. We got, let's just do one more. So put a 10 here, and a 5 here, and a 7 here, and a 20 here, and a 15 here, and a 22 here. Okay. So let's see who's here. Pool. We're converting this binary tree into an array. Okay. Who goes into element 0 in the array? 10. Good. Who goes into element 1? 5. Who goes into element 2? 20. And 7? I don't know about that. Otal, who goes into... Nope, that's actually wrong. You're doing pretty well up till that point. Who goes into element 3, Pool? Not 7. If you put 7 here, then that would be the left child of 5. Yeah, you got to put a negative 800 to indicate. I'm kidding. Don't do that. Use a bit set. But yeah, and to indicate, yeah, sure, null. 0 is probably bad. 0 is a really bad magic number to use. Use negative 82137 or something like that. It's unlikely to come up. Don't do it. Don't do it seriously. Okay, null. Okay, then 7 goes into 4, and then Zofka, who goes into 5? 15, and then who goes into 6? 22. All right, let's add one more. Megan, where does 21 go? What index is 21 going to? 13 is correct. 9, 10, 11, 12, 13. So 21 goes in here, and then 23 goes into 22. Oof. Or no, 20. I can't even read my handwriting. Whatever. You guys get it. All right. That's it for today. What? Right. 10, 11, 12, 13. I don't know. Yeah. You got it. Ran out of room there. Okay. So, yeah, whatever slot that is. Okay, now seriously. Yeah, so the left child of index 6 is going to be index 13, and the right child is going to be index 14. So that is 13 and 14. That's really, really narrow. That's it for today. We're calling it there. Thanks for coming out, everyone, and we're going to show you guys how to use this next time on Wednesday. Peace.